In this video, I'll talk about how the ancient Greek philosopher and mathematician Aristarchus measured the diameter of the moon and the distance between Earth and the moon. He did measure the size and the distance between Earth and moon during the lunar eclipse, and he used a very simple mathematical tools, that is the basic trigonometry. And first I'll talk about the basic trigonometry, the basic equation that he used. So let us consider we have a circle here, and this is the arc. R is the radius of the circle, and theta is the angle made by this arc onto the center of the circle. Then there is a relation between this radius, this angle theta, and this arc length, and this is given by here theta equals to s over r, where s is the arc length and r is the radius. So from this equation I can also write down s equals to r theta. And remember, here theta is in radian. Theta must be in radian if you use this equation. If your angle is given in degree, then you have to use this equation here. You have to divide this equation by 57.3. You might be wondering where this 57.3 is coming from. The answer lies in the relationship between the degree and the angle. Remember, pi radian is equal to 180 degree. So 1 radian is equal to 180 divided by pi, and this is equal to 57.3 degree here. Okay, so once we understand the relationship between arc length and the radius, now let's talk about Aristarchus model. The first thing you have to understand is, in his model he did all his calculation during the lunar eclipse, or his observation was during the lunar eclipse. What is the lunar eclipse? The lunar eclipse occurs when the moon moves into the Earth's shadow, and this can occur only when the sun, the Earth, and the moon are exactly aligned. Okay, so let me explain this one. Here is the sun, here is the Earth, and this is the moon here. The sun is casting the shadow onto the sun is shining the light onto the Earth, so this side will be completely dark, and as the moon enters into this shadow region, then the lunar eclipse occurs. Okay, so now what was the his assumption? Aristarchus assumed all the light rays that is coming from the sun are parallel. This all light rays are parallel, and this is very important here. This is his assumption. Okay, so his assumption is all the light rays that is coming from the Earth to the sun are parallel light rays. What does that mean? That means the shadow, as all these light rays are parallel, then the shadow that it will form onto the Earth's surface will be cylindrical. Okay, so that he assumed the shadow to be perfectly cylindrical. And what does that mean again? That means the length of the shadow will be exactly equal to the diameter of the Earth, because the shadow is cylindrical. So the length of the shadow again is exactly equal to the diameter of the Earth. And as the moon enters into this shadow, then the lunar eclipse occurs. So here is the length of the shadow is the diameter of the Earth. That is again was his assumption. So now what was his observation then? And his observation was, he calculated the time, he measured the time, he observed the time for the moon to complete this shadow here. And what he observed, that the moon takes 3 hours, 3 hours to cross this shadow here. To cross this shadow, moon takes 3 hours. And the moon takes 30 days to complete one orbit around the earth. That means the moon takes 720 hours to complete one orbit around the earth, and it takes 3 hours to complete the shadow here. What does that mean? Now we will have a relationship here. So 360 degree. So if the moon completes one complete orbit around the earth, that is 360 degree. And if we know the time here, and that time is 3 hours, from that observation we can calculate the angular width by this shadow here onto the earth's surface. So let's do here. So we will assume here the angle, this alpha angle here, is the angular width of the shadow onto the earth's surface. So 720 hours for the moon, it takes 720 hours, and that makes 360 degree angle. If it takes 3 hours, then we assume the angle is alpha. And from this simple equation, we can calculate the angle alpha, which is 1.5 degree. Okay. So the angle made by the shadow onto the earth's surface is 1.5 degree. He also measured the angular width of the moon. So let me talk here. So this is the moon here, and then the angle measured, the angular width of the moon onto the earth's surface he measured was 0.5 degree, and it is pretty straightforward to measure. In fact, you should be able to measure just by using a coin. Okay, and I will talk about in a different video. So he measured the angular width here, this is the beta angle here, onto the earth's surface to be the beta, which is 0.5 degree. So the angular width of the moon onto the earth's surface is 0.5 degree. The angular width of the shadow onto the earth's surface is 1.5 degree. What does this mean? That means this shadow, the shadow is 3 times bigger than the size of the moon. Okay, and the shadow is exactly equal to the diameter of the earth, or in other words, the diameter of the earth is 3 times the diameter of the moon. That's very simple and straightforward things that he measured. That's a very profound thing. So the earth's diameter is equal to the length of the shadow, and from the timing he calculated, from the angular width he measured that the moon is, or the shadow is 3 times the size of the moon. So 3 times the diameter of the moon here. The length of the shadow is 3 times the diameter of the moon. So S, the S here is the size of the moon, or diameter of the moon. What does this mean here? Again, the moon is 3 times, the moon size or the moon's diameter is only three times smaller than the diameter of the earth, or the earth is 3 times bigger than the moon in diameter. So now let's again look into this arc here. Okay, so we have this arc length here, and look at this angle beta. So that we're now going to find out the angle between this r theta and this s here. Let me write down s here. This is the s, that is the size and the diameter of the moon. And from the equation first that we just talked here, from this equation, s equals to r theta divided by 57.3 So just that equation I have written here. Okay, and S, this S is equal to d over 3, the d over 3. And if we solve it, then what we get, a relationship between R and the D. What is R? R is the distance between Earth and the Moon. Moon. And D is the diameter of the Earth. Earth here. So here the distance between Earth and the Moon is about 38.2 times the diameter of the Earth. So that he measured at the time. Now let's compare this with the modern measurement, the modern values. The modern measurement tells you the diameter of the Moon is 2160 mile and diameter of the Earth is about 7920 mile, and the distance between the Earth and the Moon is this much. So if I just take a ratio d over s, then what I see here is 3.7. That means the Earth is 3.7 times bigger than the size of the Moon. That is the modern measurement. The modern measurement tells you the Earth's diameter is 3.7 times bigger than the diameter of the Moon. But Aristarchus measured only 3 times. So he was quite short of this one. And if you calculate the percentage error, so this was about 19%, the percentage error in measuring the diameter of the Moon. And now let's see here R and the D. Now let's take a ratio of this one, R and D. If I just take, this is again from the modern measurement. This is the modern measurement. With the value, if I take a ratio, then what I get is 30.2. That is again the modern measurement here. So the distance between Earth and the Moon is about 30.2 times the diameter of the Earth. But Aristarchus measured 38.2 times. So again, he overestimated the distance between Earth and the Moon. And again, if you calculate percentage error, then the percentage error is 26.5%. So he was quite off. Now, why was he off? It just sounded like everything he postulated is correct. But why was there off? His calculations seemed pretty straightforward. There is nothing surprising in the calculation. So why was he off? The answer lies here. So he assumed, what was his assumption? That the shadow onto the Earth's surface during the lunar eclipse is perfectly cylindrical. And again, the idea behind this one was the sunlight that is coming from the Earth, coming from the sun to the Earth's surface is entirely parallel. All are parallel. If all the light rays are coming parallel, then it would make a complete cylindrical shadow. But that's not the case here. If you look at the true picture of the lunar eclipse, the true picture of the eclipse, this is how it should look like. Here is the sun. The light rays are coming this way, the light rays are going this way, the light rays are also going this way too. So the light rays, you see here, this is how the light rays are coming. So that means the shadow onto the Earth's surface will not be cylindrical. Rather, it will be a tapered structure. So it's a tapered structure. Okay. So that means if you compare with the Aristarchus model, it just looks like this. So that means the length of the shadow, he overestimated the length of the shadow. But in this case, in the case of true eclipse, the length of the shadow is significantly smaller than what Aristarchus measured. So that was the error. Okay, so the main source of error was his assumption that all the light rays from the sun coming to the earth's surface are parallel, or in other words, the shadow casted by the sun onto the earth's surface during the lunar eclipse is perfectly cylindrical. That's not the case. The shadow casted by the sun onto the earth's surface is a rather tapered structure. So if we take this into account, then you should be able to calculate the values here, or the modern calculated values. Okay, so but in spite of that, we must appreciate that at the time he did this calculation with a very simple observations, and although it was about 19% and 26.5% off, but his process was quite fantastic. So this is it from this video. Again, if you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel. Thank you very much.